Welcome to The Explainer. I am absolutely thrilled you're here today. Look, if you're an engineering student, a prospective undergrad, or just a really focused learner trying to figure out how to navigate the incredibly lucrative world of textile engineering, you are in exactly the right place. Today, we're putting together a definitive, step-by-step roadmap to securing top-tier industrial placements in B.Tech's Textile Chemistry. We're going to dive into everything, from your second-year syllabus right through to crushing those intense technical interview rounds and ultimately securing high-paying jobs, even overseas. Let's get into it.
But first, think about this for a second. What if the future of fashion requires a literal molecular revolution? We usually think of fashion as, designers sketching dresses or mechanical looms weaving fabric. But the reality is that the absolute biggest challenges in the global apparel industry right now cannot be solved with a sketching pad or a sewing machine. They have to be solved in a laboratory, at the molecular level, by highly specialized chemists.
And here is exactly why. 92 million tons. Just let that staggeringly huge number sink in. That is the amount of waste the global textile industry generates every single year. Not to mention, it accounts for nearly 10% of global carbon emissions. The traditional ways of wet processing, dyeing, and finishing fabrics, they're notoriously water and chemical intensive. Basically, the industry is in a state of environmental crisis. And because of this, there's an absolutely critical demand for sustainable textile chemists who can completely re-engineer these processes from the ground up. So here is the exact chronological roadmap we'll use to break this down today. First, scope and future demand. Then, branch comparisons, followed by core curriculum, study advice and internships, career progression, and we'll wrap up with salary and global opportunities.
All right, let's kick things off with Section 1, Scope and Future Demand, what I call a molecular necessity.
These right here are the specific technological frontiers driving that incredible demand we just talked about. We are talking about cutting-edge green chemistry, waterless supercritical carbon dioxide dyeing, bioengineered smart materials, and nanotechnology finishes. And here's the kicker. Because this is such a niche field, and because there are far fewer textile chemists graduating every year compared to, say, mechanical or computer science engineers, premier institutes are consistently hitting 80 to 100% placement rates. While other engineering branches are suffering from oversaturation, textile chemistry grads are literally being scooped up by recruiters because they possess these specific, highly sought-after green tech skills.
Moving right along to Section 2, Branch Comparisons Explained.
Now, you absolutely must understand these academic distinctions to succeed when you're sitting across from a technical recruiter. Let's break it down. Textile technology, that's about the mechanical conversion of fibers into yarns. Think high-speed spinning. Chemical engineering deals with large-scale reactor design and fluid mechanics. Polymer science is focused on synthesizing plastics and rubbers. But textile chemistry, it is highly specific. It focuses on molecular wet processing, fiber modification, and dye synthesis. Knowing exactly where your expertise fits into the broader manufacturing puzzle is going to give you a massive advantage during those interviews.
The fundamental dichotomy is actually pretty clear. Textile technology is heavily mechanical. Go that route, and your job title might be spinning master, working directly with industrial looms. But textile chemistry is purely molecular. You'd be a textile chemist or colorist, working in analytical labs with spectrophotometers and organic dyes. You aren't physically building the fabric. You're fundamentally altering its chemical properties, giving it color, making it flame retardant, or adding water resistance.
Okay, Section 3, Core Curriculum and Skills. Let's look at what you're actually going to study. This isn't just your basic high school science. Check out an actual university syllabus for this major. You've got computational differential equations, organic chemistry, polymer chemistry, and thermodynamics of dyeing. It's a seriously rigorous blend of applied chemistry and chemical engineering unit operations, entirely designed to turn you into an elite problem solver.
Chronologically, this journey builds up in very distinct phases. Your first year is usually general engineering, but in year 2, you dive headfirst into fiber physics, understanding the actual macromolecular structure of things like cellulose and polyester, along with preparatory processes like bleaching. Year 3 shifts to the technology of dyeing, printing, and learning about the massive machinery used for chemical processing. And finally, Year 4. This is where you tackle the real cutting-edge concepts: advanced chemical processing, environmental management, and eco-friendly finishing techniques.
Which brings us to Section 4, Study Advice and Internships. This is where strategy really comes into play.
Listen, if you want to secure a top-tier placement, you cannot just memorize textbook definitions. It just won't work. Technical interviewers from global heavyweights like Huntsman or Arvin Mills are going to intensely test your foundational understanding. You've got to focus heavily on thermodynamic and kinetic mechanisms. You absolutely must understand exactly how a chemical reaction pathway works when a dye binds to a fiber at different temperatures. Get into the laboratory early. Real success in campus recruitment means deeply understanding these molecular mechanisms and being able to clearly explain how you'd solve a green chemistry problem directly on a high-stakes production floor.
And here is the absolute golden ticket: strategic industrial internships. Why? Because early industry internships are the direct mechanism leading to permanent pre-placement offers, or PPOs. Think about it. When a company sees you successfully applying your academic knowledge of dye synthesis or quality control in their actual lab during a summer internship, they are highly likely to offer you a permanent, lucrative role well before you even walk across the stage at graduation.
All right, let's map out that future. Section 5, Career Roles and Progression.
Here is your literal career ladder. You'll typically start out at Step 1 as a production trainee or lab assistant, really focusing on process control and testing. Give it 3 to 6 years of proven experience, and you move up to Step 2, taking on mid-level management roles like dyeing and finishing manager or lead textile chemist. Finally, as you build deep industry expertise, you advance to Step 3. These are the highly lucrative senior technical roles, like a chemical compliance officer ensuring global environmental standards are met, or an R&D executive developing the very next generation of smart fabrics.
But let's zoom back to day one on the job. Your entry-level responsibilities are going to depend entirely on your sector. If you ended up in a mechanical spinning or weaving sector, you'd be tracking things like yarn twist and loom efficiency. But in your core domain, the chemical processing sector, your day-to-day will be as a lab assistant or process engineer. You'll be right in the thick of it, focusing on precise dye formulations, testing color fastness, and strictly monitoring the pH levels of massive wet processing baths.
Finally, let's talk numbers. Section 6, Salary Insights and Global Opportunities. In the Indian private sector, freshers can generally expect an entry-level package between 3.5 to 6.5 lakhs per annum. As you step up into mid and senior domestic roles, that easily jumps up to between 12 and 18 lakhs, and frankly, often higher for niche R&D roles. But the real game changer is when you look globally. Because global markets and developed nations are governed by high-performance materials and incredibly stringent environmental safety standards, specialized textile chemists are highly valued. Overseas roles in the USA, Canada, or Germany can easily command equivalent salaries of 25 to 55 lakhs per annum for process engineers and R&D chemists.
And you aren't just limited to one type of employer. You've got a very distinct choice. You can go to massive private sector recruiters like Arvin Mills, Raymond, or global brands like Levi's, working as a process engineer or compliance officer. Alternatively, you can go after highly stable government roles through the Ministry of Textiles or the UPSC. Securing positions like Deputy Director of Laboratories or Quality Assurance Officer offers fantastic job security and really robust pay scales.
So we've covered the curriculum, the interview strategies, the career paths, and the salaries. But I want to leave you with this final thought. Will you be the one to engineer the next self-healing fabric, or maybe a completely waterless dye? The textile industry is facing a massive sustainability crisis, and they desperately need molecular problem solvers right now. Think about the immense potential you have to shape a sustainable future and build an absolutely incredible career with this roadmap in hand. Thank you so much for joining me on this explainer, and keep learning.